When you scale up rotating machinery to an industrial level, the physical forces acting on the metal become immense. A massive turbine rotor like this carries extreme rotational inertia. But if that machinery is driven by a standard internal combustion engine, it faces an immediate physical problem. An engine does not produce a continuous, smooth flow of torque. Power generation is violent, localized, and highly erratic. To prevent an engine from tearing its own driveshaft apart under these alternating stresses, engineers have to control its speed at two completely different operational scales, using two highly specialized devices, the flywheel and the governor. Understanding the exact mathematical division of labor between these two components is the absolute foundation of stable rotational machine design. This diagram is the primary mathematical tool for analyzing that erratic torque. We map the crank angle on the x-axis across a full 4π four-stroke cycle and plot the resulting torque on the y-axis. For the first half of the cycle, the engine actually consumes power. The suction stroke draws a slight negative torque, followed by a much deeper negative drain on the system during the compression stroke. Then combustion hits. The expansion stroke generates a sudden, massive positive spike in torque, reaching its absolute peak at Tmax. Finally, the exhaust stroke requires another brief period of negative work to force the spent gases out of the cylinder. If you calculate the total net area under this complex curve across the entire 4π duration, you get the total work done by the engine over one complete cycle. When we average out that total work over the cycle duration, we find the mean torque. This strict horizontal line represents the steady, continuous baseline of power that the driven machine actually requires to operate. That mean line is our theoretical equilibrium. Every spike and dip diverging from it represents a physical imbalance in the system that will shear the metal if left unchecked. Look at the specific area of the expansion curve that protrudes above the mean torque line. This area represents excess energy. Because the driven machine doesn't need this sudden surge of power, the surplus forces the crankshaft to aggressively accelerate, violently whipping the rotation forward during every single expansion stroke. The flywheel is the dedicated hardware engineered to solve this. Its sheer physical mass is scaled to absorb this exact geometric area of excess energy. It acts as a kinetic reservoir. It stores that surplus energy as rotational momentum during the expansion spike, and then bleeds it back into the crankshaft during the negative suction, compression, and exhaust strokes, pulling the torque back up toward the mean line. Because of this loop, the flywheel is strictly a micromanager. It operates within a single cycle to smooth out internal kinetic variations. But what happens if the external load on the machine drops entirely? If a factory shuts down a heavy process, the required mean torque for all future cycles permanently shifts downward. The flywheel is mathematically incapable of adapting to this. It cannot maintain a constant mean speed over time. If the load decreases, the engine will simply run away, spinning faster and faster across every subsequent cycle. This is where the governor takes over. Operating entirely outside the individual engine cycle, the governor physically throttles the fuel supply in response to load changes, restricting the energy input until a new, safe mean speed is established. And just as the flywheel cannot control the long-term mean speed, the governor is far too slow to react to the micro-fluctuations occurring inside the four-stroke cycle. The engineering boundary is strict. The flywheel manages the thermodynamic output by storing kinetic energy. The governor manages the thermodynamic input by metering the fuel. Look at this turning moment diagram to extract the parameters needed to size a flywheel. By finding the mathematical difference between the absolute maximum and minimum kinetic energy states during the cycle, we isolate the maximum fluctuation of energy. Engineers take this energy delta and use it to calculate the exact mass and radius of gyration required to keep the coefficient of fluctuation of speed safely within operational limits. If a flywheel is sized incorrectly and this coefficient strays out of bounds, the relentless cyclical stress of the expanding gas will result in catastrophic material fatigue along the shaft. A robust engine design requires a perfect pairing of micro and macro controls. The flywheel absorbs the violence of the explosion, while the governor dictates the pace of the machine.